I am Maglunob, a third-year BSECE student in Iloilo Science and Technology University.
So today, we will discuss about the T flip-flop. So, first, we will have the definition of flip-flop. So, flip-flop is an electronic circuit with two stable states that can be used to store binary data. The stored data can be changed by applying varying inputs. Flip-flops are fundamental building blocks of digital electronic systems used in computers, communications, and many other types of systems. So there are many different types of flip-flops, and one of those is the T flip-flop. So what is the T flip-flop? So T flip-flop is also known as toggle flip-flop. To avoid the occurrence of intermediate state in SR flip-flop, we should provide only one input to the flip-flop, called trigger input or toggle input. Then, the flip-flop acts as a toggle switch. So next is the symbol. So in our symbol, basically, the T flip-flop is derived from JK flip-flop. So here we can see that our J input and K input are shorted, which makes it the T or the toggle input. So here is our simplified T flip-flop symbol, where the J and K input is replaced with T input. So T input means toggle or toggling, and toggling means changing the next state output to the complement of the present state input. It means that, for example, if our input is 0, then the toggled input will be 1, and if the input is 1, then the toggled input will be 0. So here in the symbol, we have also the clock and the Q and the Q bar. So next is our logic diagram using NAND gates. So here is our T flip-flop diagram using NAND gates. So if you can see, in our diagram, we have two 3-input NAND gates and two 2-input NAND gates. And in our two 3-input NAND gates, we have two common input, which is the T or the toggle and the clock. And here in the upper NAND gate, we have the input connected to the Q bar. And here in our lower NAND gate, we have the input connected to the Q. And here next is our 2-input NAND gate. So in our 2-input NAND gate, the upper 2-input NAND gate, the first input is connected to the upper input NAND gate, and the second is connected to the Q bar. And here we have the input connected to the lower NAND gate, and here the input connected to the Q. So here is our characteristic table that is derived from our logic diagram. So here our T flip-flop characteristic table derived from our logic diagram. So here we have 4 combinations of Qn and T. Qn equals 0, T equals 0, Qn equals 0 and T equals 1, Qn equals 1 and T equals 0, and Qn equals 1 and T equals 1. So here, if we will look in the table, if T equals 0 and Qn equals 0, our Qn plus 1 or Qnext is equals to 0. If T equals 1 and Qn equals 0, then Qn plus 1 or Qnext is equals to 1. If T equals 0 and Qn equals 1, then our Qn plus 1 is equals to 1. If T equals 1 and Qn equals 1, then our Qn plus 1 is equals to 0. So if we will understand this table, we can conclude that when T is equals to 0, our Qn plus 1 or Qnext will be in memory state, or it will just retain the value of our Qn. And when T is equals to 1, it is in toggle states, which means that the value of Qn plus 1 will be the complement of our Qn. So here, when T is equals to 0, and here, our Qn plus 1 is the same with our Qn. And when t is equals to 1 here and here, the value of our qn plus 1 is just the complement of our qn. So next is our equivalent equation. So here's our equivalent equation. So here is our equation. Qn plus 1 is equals to t qn bar plus t bar qn. So in this equation, we will look if it will agree with our characteristic table. So let's see. If t equals 0, then qn plus 1 is equals to 0 times qn bar plus 1 times qn. So 0 times qn bar will be just cancelled out, and it will give us qn plus 1 is equals to qn. And it agrees with our characteristic table that when t is equals to 0, it will be in memory state. And if t is equals to 1, then qn plus 1 is equals to 1 times qn bar plus 0 times qn. So it gives us qn plus 1 is equals to qn bar. And it also agreed with our characteristic table that if t is equals to 1, then our qn plus 1 will be in toggle state. And lastly, we will have our electronic workbench simulation.
So this is our simulation, and we use NAND gates in master-slave configuration JK flip-flops, and we have preset and clear inputs. So let's start simulating. So first, we will enable the oscilloscope to see the graph. So if both preset and clear is on, Q and Q prime are blinking, which means that the T flip-flop is free to respond to the value of trigger and clock inputs, and we can see that the clock operation takes place. And if the preset is off and the clear is on, the clock input cannot take in action, and Q was set to 1 while Q is blinking. Moreover, if the preset is on and the clear is off, the clock input cannot take in action, and Q is set to 1 while Q is blinking. If both the preset and clear is off, we have an undesirable output because they are both 1, and it is called race condition because Q and Q prime should have opposite value because Q prime is the complement of Q. So that's all. I am Manuel Maglunob. Good day and